This is Mr. Sida. I'll be doing chapter 6 today. We're dealing with quantum theory, and you should be familiar with light calculations and Planck's equation. And I'm going to start off by explaining where line emission spectra comes from. And the goal of the chapter is to describe where the electrons are in an atom. And it's a little bit complex, and it involves some wave functions and some abstract thinking. So I'll start with the sheet that I gave you on quantum calculations number 2, because this actually is going to include some of the light equations. And the whole chapter starts with light and the study of light. And the unit of light is energy, is a photon. And a photon is defined as a packet of energy. Okay, I'm going to start by proposing that we look at a hydrogen atom. And you're going to recognize a few of the atomic models that we dealt with early in chapter 2. If I simply say I have a hydrogen atom and I have a single electron at energy level 1 orbiting in a hydrogen atom, okay, there's one proton, and I can input this state that it's in is called the ground state. Okay, if I was to input energy as light going in to that electron, the light going in causes the electron to gain energy, and that electron is able to jump up into a higher level orbital, and that's called the excited state. Now this energy would be of a certain wavelength and a certain frequency. Okay, the difference between here, this would be, say, energy at level, I'll call it 5, and this is energy at level 1. The difference between the two, that's your change in energy going from 1 up to 5. That's the energy that we use in Planck's equation. Okay, so an electron can be the first quantum number is energy level. And so if I look at a periodic table, N is equal to your energy level. It could be 1, 2, 3, all the way up to 7, all the way up to infinity. Okay, but your energy level is what you see on the periodic table as a number labeling each period. This is energy level 1, 2, 3, 4, 5, 6, and 7. A lot of times if I have a periodic table, I'll write them over here on the right hand side. 1, 2, 3, 4, 5, 6, and 7. So that is your first quantum number, energy level. It refers to each period going across, and only the main groups, here and here. When you get in here, well, the orbital in here appears to be filling level 4. It actually applies to level 3, 4, 5, 6. Okay, it simply fills after you fill this level. You start to fill the 4, you fill the 3, and then come back and finish the 4. These inner transition metals, I go here from a 55 to a 57. If I'm here at level 6, this level actually is a 4 and a 5. So These refer to filling inner levels in electrons. We'll get a little clearer picture of that later on. I just want you to know that that's where our N number comes from. As you fill up, that's 1 electron in hydrogen, 2 electrons in your level 1, and then level 1's full. If you're going to have any more electrons, they have to go in level 2. It's kind of like a hotel. Now, there's many other energy levels that could be filled. You could fill energy level 2, energy level 3, energy level 4, all the way up to energy level 6, and potentially I could just keep going. Now, absorbing energy is going up, and so this represents going up is an absorption of energy. In chapter 5, we would have called that an endothermic process, absorbing energy. Okay, as the electrons go up to an excited state, they're capable of dropping down. So Joseph Balmer, better get that right, Johann Balmer. He was a Swiss school teacher. And he noticed that where light came from, when these electrons go up, we're absorbing light, and that's what happens if you're in a light atmosphere. Going down to level 2. So you could drop from level 3 to 2. You can drop from level 4 to 2. You can drop to level 5 to 2. You could drop to level 6 down to 2. Okay. These level drops, correspond to a different frequency of light giving off, to a different wavelength. So as this drops, you would spit out a photon, and when you would give off red light. The level 4 drop, you would give off at a specific wavelength, a specific energy. Again, the distances from here to here is your delta E. And this would correspond to a blue-green light. And this is where your line emission spectra comes from. If you look at line emission spectra, you see for hydrogen gas, if you put that light through a prism, it separates it, and you get a distinct one red line, and then nothing but blackness in between. Then you get a blue line, a blue-green line. Then you get a darker blue line. That's blue light. And then finally, your highest energy would be your highest frequency, and this would be violet light. So corresponding to your level drops, the lowest drop was red. So red is your lowest energy level. Violet is your highest energy light. Okay. Now what I'm going to do is I'm going to calculate the wavelength of light emitted from an electron dropping. Now, it is emitted because it's going down. It's an exothermic process from n equals 6 to n equals 2. And this is going to take all the calculations that I've shown you. Now, the first equation and you're going to be given several equations. It's called the Bohr equation. And I wasn't sure. I always kind of learned also that Balmer came up with this equation. And that's calculating the energy at any level. And this only works for hydrogen. But it's kind of cool that we can do it for any atom. But for hydrogen, there's a constant number, negative 2.18 times 10 to the negative 18th joules divided by the energy level squared. And that's how I can calculate the energy at level 6, and I can calculate the energy at level 2. Then I'm going to find that difference in energy. Finding that difference in energy is going to allow me to tell me this frequency of wavelength that comes off, and it's going to allow me to tell me the color of light that comes off, which is all pretty cool. I would say those are all quantum calculations. Okay, so we'll start off by saying the energy at level 6 is equal to negative 2.18 times 10 to the negative 18th joules over 6 squared. We'll also calculate the energy at level 2, which is equal to negative 2.18 times 10 to the negative 18th joules divided by 2 squared, which is 4. Okay, so with those two calculations, you got negative 2.18 negative 18 divided by 36. And here I get negative 6.05 times 10 to the negative 20 joules. Okay. If I divide it by 4, I get negative 5.45 times 10 to the negative 19th joules. This is actually a lab I would have you calculate if we're back in school. And it just involves these calculations, and then we would actually do our observations. The difference in energy, the delta E, it would be 6 subtracting 2. So what I'm going to do is I'm going to simply subtract these two numbers. Now, this number, negative times a negative in the negative 19th, is larger than this number. So your answer is going to come out to be positive. And a positive number is an exothermic process. But what it really means is that light is emitted. If this number comes out negative, that would be light absorbed, an endothermic process. And what's funny is that your delta E corresponds, in chapter 5, we learned about delta H. Those two numbers correspond to each other. They're just in different units. Delta E is joules per one atom, or one photon, or one electron, okay, or even a molecule. Delta H was in kilojoules per mole. So delta H is a much larger magnitude number. Delta E is a very small magnitude number. So let's go ahead and subtract these two numbers, okay. So like I say, this number, the larger magnitude, is positive, and I'm going to subtract the smaller number. And you always want to use E in your calculator like I've taught you to do. Try not to use little caret. It makes it much easier to do all your calcs, including subtraction with E. It won't mess it up. Your difference is 4.85 times 10 to the negative 19th joules. Now here goes, this is now going to link you into the other worksheet number 1 that I gave you. I'm going to take that energy and I'm going to turn that energy into a wavelength. Well, in this chapter, very simply, we're smoothly going to go from an energy to a frequency to a wavelength, lambda, mu. To go back and forth from energy to frequency, you're going to use Planck's equation, delta E equals hv. To go between frequency and wavelength, we're going to use the light equation, speed of light equals lambda times v. And so all the time we'll just be going back and forth, and this should be very smooth. It shouldn't be a problem. It should be just an exercise. So the first thing I want to do is find mu, frequency of the light. I might add one thing. With your negative and positive numbers, it's impossible to get a negative frequency, and it's impossible to get a negative wavelength. And the negative really corresponds to the energy either coming in or going out. Energy coming in is the electron going up. That's an absorption. Positive is the electron going down, and that would be the emission of light. So even before you start a problem, if you know you're going from a lower number to a higher number, you know that's going to be an absorption. A higher number going to a lower number, that's going to be an emission. So you can cut out all the signs and just go right to whether you know whether it's coming or going. To find frequency, we're going to use Planck's equation, delta E equals hv. So we're going to solve for nu. And as always, I like you to not plug in numbers, but solve for your letters. Nu equals delta E divided by h. So it's 4.85 times 10 to the negative 19th joules. And h is Planck's constant, 6.63. It's a constant that will always be given to you. Just a very small number, 10 to the negative 34th. And it's joules times seconds. The joules cancels out. Your unit becomes 1 over second, which really refers to 1 wave per second. Or physicists would like to call that a hertz. In chemistry, hertz doesn't do much for me. I'd rather know it as waves per second or 1 per second. It's the same thing you have when you listen to a radio station. Your dial number, if you're in FM, it's 10 to the 6 waves per second. So if you're listening to 99.3, that would be times 10 to the 6 waves per second. On the AM dial, it's kilohertz, so it's times third to the waves per second. All right, our number, frequency equals and on your calculators, you really want to be able to smoothly go back from scientific mode to normal mode. Small numbers like this, you definitely want to be using scientific notation on your calculator. You want to have science. The answer is 7.31 times 10 to the 14th, and a unit is 1 over seconds. And one thing I might mention, visible light. Visible light is always of a magnitude of 10 to the negative 19th joules. And I might say something about that unit right there. It's always joules per photon, per atom, per electron, or per molecule. I meant we don't always put that on there, but it's implied that it's per 1 photon going up and down. So this is the energy of that 1 photon, the frequency, 7.31 times 10 to the 14th. Visible light in frequency is always of a magnitude of 10 to the 14th. And the next thing we're going to do is find our wavelength. And your Greek name for that letter right there is called lambda, corresponds to a small l. This is nu, corresponds to a small n, nu. Okay. And so when I find wavelength, I go from energy to frequency. Now I go to wavelength. I use the light equation, C equals lambda times nu. Solve for lambda. It's the speed of light over the frequency. Speed of light is a constant, 3.00 times 10 to the 8th. The unit is a meter per second. I'm going to divide that by 7.31 times 10 to the 14th. That's 1 over seconds. Your seconds cancels out, and the unit will be meters. And here it is for visible light. You get 4.11 times 10 to the negative 7th meters. Now, usually on our scales, when you look at a spectral chart, your wavelengths are often given to you in nanometers. Okay, so I'm going to convert meters into nanometers. And if I gave you the opposite task, you could start with nanometers. You always want to go to meters because your speed of light will be in meters per second. It is possible to use nanometers, but your speed of light would have to be in nanometers per second, which is 10 to the 17th. It can be converted. You would go backwards to frequency and then go back to energy. So you can go forwards and backwards with these equations. So we got 4.11 times 10 to the negative 7th meters. And I'm going to go meter to a nanometer through dimensional analysis to nanometers. And I got 1 to 1 times 10 to the 9th. And your visible wavelength is in the hundreds in nanometers, and your answer is 411 nanometers. That corresponds to violet light. Okay, and you could do the same exact calculation, and what you would have done, we just did 6 to 1, so this light is 411 nanometers coming off. And I'm going to try and show you, I'm going to take this off. I usually have this hooked up, but I'm going to take this to my computer because I'm ready to shut this video down. And I just want to show you, if you look up the emission spectrum for hydrogen, I had 411, but 410, and it would have just been sig figs and rounding. Actually, I rounded up when I should have stayed. It was an even 5. But if you did the blue, this one's 6 to 2. There's 5 to 2. You would have got 434. 4 to 2, 486. That's your blue-green light. And your red light, 656. So I think that's pretty cool that you can go in from the energy levels and calculate all those numbers. And this is one of the reasons why, when they went to discover, this was all discovered in the early 1900s, and when they discovered helium, it was the spectra of helium that they discovered, and they discovered it by looking at the sun with the spectroscope, just looking at the light coming from the sun. And this is also why you can look at any star today, put a spectroscope on it, see this is like a fingerprint for elements. And so, if you see the intensity of all these lines and where they're at, you can tell how much hydrogen is on it by percentage. You can tell how